Okay, everyone, let's try to get started now. It's been a long time since I've been in front of this many people at once. My name's Robin. I'm your tutorial TA for September. Hello. And after September, another TA will take over the tutorials. I'm also the one marking problem set 1, so if you have any questions or comments about that, here's my email. You can email me. Some of you already have. One of the questions I'm getting a lot about problem set 1 is whether you can do them on your iPad and sort of just export a PDF and send that in. That's totally fine. As long as you send me a PDF of some sort that I can actually open and discern your handwriting and whatever, then it's fine. I work in Professor Diller's microrobotics lab as a master's student. My research is on these cell-scale microgrippers that you can ask me about later if you're curious. And I went to my undergrad at Waterloo, did mechanical engineering. Yes, I know. Okay. Waterloo's better, but you know. Okay. So I graduated in 2018, and then I worked in industry for a few years before starting my master's here. And I took basically the exact same course at Waterloo. Actually, it was my best course of my whole undergrad, but I've forgotten a lot of it, so I'm reviewing kind of with you guys. And the last thing I want to mention is that we're trying to record the session. You can see the camera at the front. Hopefully it works out and my audio gets recorded somehow, either through the camera or apparently the podium's supposed to be recording my audio right now. And we'll try to get that uploaded so that if you have to miss a tutorial or if you have to leave early, you can still access that content. So the format of the tutorial is, this slot is 2 hours long, but I hope that the content doesn't take the whole 2 hours. I want to leave some time at the end for any questions that anyone has. So I'm just going to be going over a few examples. And at any point during the examples, you can raise your hand, ask a question. I don't mind at all. And we'll see how many examples we can get through in the time that we have. And at the end, like I said, hopefully we have some time for questions. Okay. So we're going to start with drawing kinematic diagrams. And we're going to start with this backhoe mechanism, this digger. So you just sort of look at the diagram, and you can see that there's a few links that we have to keep in mind, and a few hydraulic cylinders as well. You might recognize those from your problem set. So we'll talk a little bit about how to deal with those. I'm hoping that I can just keep this up and draw on the blackboard at the same time. Can everyone see the lower blackboards? Yeah? Okay, if there's a problem with the light bleed coming over the edge of the projector screen, just let me know. I can turn it off. Okay, so I'll start on this side. So when you're looking at this backhoe, usually what you want to start with is the ground. What links are fixed in place. So you can see sort of at the bottom left there, that would be connected to the rest of the machine's body. And we can basically consider that ground for the purpose of looking at this mechanism. So it looks like there's maybe one big pin that this larger long truss on the left side pivots around. So we'll draw that in first. And since it's in the bottom left, we'll start here. So that's sort of the pivot point. And we'll signify that it is fixed to ground with this familiar symbol. So next, we're going to take a look at this link that's sort of on the vertical on the left-hand side. And what sort of pivot points are in this machine. So it looks like there's 3 pins, and we're not really sure exactly what it looks like the hydraulic cylinder might be connected to the middle one, and then the next link is connected to the upper one. And this back one is not shown in the diagram, but that would be connected to another hydraulic cylinder that allows the whole arm to move back and forth, but we'll be omitting it for this one. Okay, so if there's 2 pivot points, we can start by drawing those in. And I'm going to be starting with a stick diagram, and we can also talk about how you might draw this for a non-engineering audience as well afterwards. Okay, so it looks like It's roughly in like a long triangle shape, so I'll draw one pivot point here, maybe one up here. And then it's just a matter of connecting these pivot points. So one way that you might do that is just connect them all in a triangle. That would be totally fine. Like this. And because we want to signify that this is all one link, it's not 3 links connected in a triangle, we would do some shading. So you could either shade the whole thing in, or you could just shade in the corners. Whatever you find easiest. But once you've done that, it shows that this is just one large link. OK, so that's the first link done. Or maybe the second if you consider the ground link as one. So next, let's take a look at the link that sort of comes down from that top pivot point towards the bucket. So it has to be connected at this pivot point here. And then there's another pivot point up top, which is connected to the hydraulic cylinder. So let's draw that one in. Almost running out of space here. And then there's another pivot point for the other hydraulic cylinder. Seems to be about over here. And so this isn't a drawing to scale, right? For the purpose of like these types of diagrams, what you're really trying to get across is the rough shape of it and how it works. It doesn't have to be to scale. So you don't have to take out like a ruler and draw this exactly. If you wanted to do like a complex analysis of exactly how the mechanism moves, then you might want to draw it to scale. And that'll probably come up later in the course. But for these diagrams, we're just trying to show how it works. OK, so this link also has one more pivot point sort of at the bottom, and that's where the bucket attaches to it. So maybe that's down here. So again, this is all one link, and we can draw lines to connect them. And just like the last one, we probably want to do a bit of shading to signify that this is all one solid body. Maybe something like this. OK, so it's already looking kind of like a digger. Let's get the bucket in place before we talk about the hydraulic cylinders. So the bucket has this, like, if you see the yellow part of the bucket link, it's kind of curved. But what's important is where the pivot points are, right? Like, we don't really care what the material in between looks like, at least not for a stick diagram. What we care about is where the pivot points are, because that's basically where all the action's happening. That's what causes the mechanism to move the way it does. So we'll just draw the next pivot point here. And we can draw a stick connecting them. And so this is basically like the bare bones. Like, we haven't drawn in the hydraulic cylinders yet, but we should probably draw in the bucket, because even an engineering audience might wonder what exactly is like at the end of this thing and how is the bucket oriented. So it looks like the bucket is facing down, so we'll just kind of draw like a bucket shape like this. That should be good enough. And we might want to just like lightly shade this in somehow. OK, so now for the hydraulic cylinders. So when you look inside a hydraulic cylinder, like if you've ever looked at a cross-section of a hydraulic cylinder, it's basically like a big piston chamber with a sliding piston and some fluid, hydraulic fluid, inside. So looking at the diagram here, there's like a thick part and like a thin part of the hydraulic cylinder. So for the thick part, we can draw that as like the sort of outer shell of it. You can start with just a little stick, and then here's maybe the outside of the hydraulic cylinder. And for the inside, we can draw something like this, maybe. This is like the roughest schematic of a hydraulic cylinder, but if you showed that to an engineer, they'd probably understand what it is. If you wanted, you could label it. hydraulic. And we can do the same thing for the other one. So something like that. It'll be really clear that it's a hydraulic cylinder. Okay, so that's a stick diagram. You can already see, just from this diagram, it's already pretty easy to see what's going on. And it's easy to see that, this hydraulic is responsible for the angle of the bucket head. And this hydraulic is responsible for lifting this whole length here up and down. And normally there would be, another pivot point here maybe, with like another hydraulic cylinder like this. And that would be responsible for lifting the whole thing up and down. But it's not shown in this diagram. Okay, so your problem sets talk about drawing both stick diagrams as well as more fleshed out diagrams for a more general audience. So let's give that a try. Does anyone have any questions about this? Yeah.
When you were starting off with the drawing, when you were talking about the first hydraulic in the top left,
Yeah.
you said that the hydraulic is connected to the middle pin. How do you know it's not connected to the back pin? Because it's not shown, right? Like,
It's not shown, no.
make the assumption.
Yeah, you can make an assumption about this one. Ultimately, I don't think it really matters because it doesn't affect the way the mechanism moves very much.
Right.
So in this case, I just assumed based on what I could see. Okay, any other questions? Yeah.
In the problem set, there were spring joints.
Yes.
There were motor joints.
Yes.
Is there a specific way of drawing these, or do we draw them as regular joints?
Stay tuned to the next example. It's all according to plan. Okay. Any last questions? Yeah.
So when you connect two links that don't have turning point or anything, the two lines intersect? Is that all?
Sorry, can you repeat that?
When you have two links connecting, but there's no turning point or anything, you just like you drew the back hydraulic as just being like a line connecting to it.
Oh, yeah. So yeah, another way that you could draw this, actually, as long as it's clear that it's one link, then it's fine. But there's another way that you could draw this particular link, which is you could just have this one stick here, and then another one like this, connecting to the pivot point. And if you just showed somehow that it was one link, maybe by like shading in these corners a little bit, and that's still clearly one link, right? So it's just another way of doing it. Whatever suits your style. Okay, let's try drawing the same thing, but for a more general audience. Okay, so the key with drawing these things for a more general audience is basically you're including more detail. Detail that's not really necessary to understand how the mechanism moves, but detail that more clearly shows what exactly is going on, what do these things look like in real life. Because if a non-engineering person looked at this diagram, they might not know how to interpret it. They might not know that those are hydraulic cylinders unless you explicitly told them. They might not even know what a hydraulic cylinder is. So if we draw something that looks more like what they've seen in their own experience, then they're more likely to understand it, and that's an important skill. Yeah?
Sorry, can you just draw like the numbers on it to get they're like labeling the numbers?
Oh, yeah. So I'm actually going to, yeah, I can. But I was going to do that with the mobility afterwards. But yeah, actually that's a good exercise. So we always start with the ground link, right? Ground link is number 1. I'll put the numbers in circles. And then for the rest of the links, there's really no particular way that you need to go about it because you're really just numbering them so that you can talk to them. Like you want to be able to refer to like link number 2 or link number 3. As long as it's clear which one you're referring to, then you can number them however you like. But I like to start from the base link and sort of just like move through the mechanism. So The next link, I'll just number 2. Maybe this one, I'll number 3. And then the bucket, I'll label number 4. And then to deal with these hydraulic cylinders. So, with these hydraulic cylinders, you can kind of think of them as like 2 links, right? One link is like the outer part of the hydraulic cylinder, which is like down here. And then the other link of the hydraulic cylinder is here. So we could number those 4. Oh, sorry, I already used 4. 5, 6, and do the same thing for the other one. 7, 8. So that's one way to think about it. And I'll use this as an example when we get to the mobility discussion. Yeah?
I just have a question about the 5, 6, 7, and 8. Why do you like name them like different numbers, although I think they do the same thing, or am I wrong?
We use different numbers just so that when we get to the mobility discussion, we can more easily like count what connections there are, what kinematic pairs there are, and sort of keep track of like what we've already counted so that we don't miscount.
So would this be not a redundancy?
I don't think so, no. Yeah. Redundancy is more about constraints, right? Like if 2 constraints do the exact same thing, those would be considered redundant constraints. But in this case, I don't think there's any redundant constraints here. Okay. So let's try to draw the same thing, but for a more general audience. So basically, instead of drawing symbols like this, we might want to draw like what the body actually looks like. So in that case, we could draw maybe like this connection here. So I'm trying to draw the actual shape of the object and not just a stick representation of it. For the next one, looks like it's kind of vaguely banana shaped. So maybe something like this. It kind of loops around. And then it comes back down. We can draw these connection points. And then for the following link, it has like a loop like this, something coming down like this, and then down towards the digger head. Yeah. And the last one, so the last one I just drew a straight line connecting like the 2 pivot points. But in this case, I'll draw it to reflect what the actual mechanism looks like in real life. So it's kind of got this boomerang shape. And that's connected to the digger. And then we can just draw in the hydraulic cylinders, but this time we won't use a stick representation. We'll draw the cylinder more as it is in real life. Okay, and with diagrams for general audiences, you definitely want to be more liberal with labeling. So this would be like, you could label this part as vehicle body. Let's see. You definitely want to label both the hydraulic cylinders. Maybe the digger bucket. I would say that's a more suitable drawing for a general audience. Like if you were in a meeting with management and they didn't have an engineering background, you could sketch something like that instead of something like this. It'd be easier to understand. Okay, any questions about this backhoe mechanism? Yeah?
Can you explain why there's like 2 nuts at the base and you just drew 1 pivot point, and there's also 3 nuts at like that arm that's vertical, and you just drew 2?
So I didn't include the one at the base. I think that's just like, it's hard to tell what purpose it serves from this diagram, but I think it just limits like how far this arm can come this way. So it's like a hard stop. I guess for the more general audience drawing, yeah, you could include those things for sure. So why don't I go and do that? So you can include those there. For this one, I didn't include them because they don't serve any purpose in discussing the kinematic motion of this object. And that's what this drawing is all about, is examining just the kinematic motion. Yeah?
How do you deal with electric motors?
Electric motors. So the electric motor would probably be connected to a pivot point, right? So what you could do is just label that point and say, there's a motor here, it's driving link number 2 or whatever. Okay. Yeah. Okay, any other questions? Okay. So just put this up. And we'll go to the next example. Okay, good. Okay. So this example is probably a little bit shorter, but it does have some struts, which maybe are kind of like springs. I know the spring question in the problem set might be a little tricky. When I was trying out the problem set myself, I also found it, kind of thought-provoking. The idea there is you should try to find like a reasonable approximation, some way to like reasonably approximate the behavior of the spring, or otherwise indicate its existence somehow. Yeah, the idea is just like good communication. Okay, so let's just quickly try to draw this diagram here. It's not as complicated as the other one. So this is the landing leg from the Apollo lunar landers. And looks like it's basically just a simple 4-bar mechanism, right? It's just one of the bars is extended to attach to the foot. So let's draw it in the extended position. So we'll start with ground, which in this case exists at 2 points, and we'll call ground just like the rest of the vehicle body. So let's draw the leg first. So we can just draw basically a long straight line for the leg. Maybe here we can say that it's just connected to a foot. And we'll draw the 2 connection points. Space right here. And it looks like that upper connection point is connected to the vehicle body, so we'll just say that's ground. Okay, so next let's draw what's labeled the secondary strut. It's coming off of this middle point here. This. And then it has one more connection to another ground point. Okay, so that's what it kind of looks like in the deployed position. You can see it's like a 4-bar mechanism, right? Like there's these 3 links here, and then the 1 ground link makes a 4-bar mechanism. So in this case, there's these 2 struts, right? Like this is the primary strut. And the secondary strut is this one. So I think I was researching how these struts work on the Apollo landers, and I think in reality there's like basically a compressing, it's like a car's crush body. It basically just absorbs an impact force because they don't need to really spring back. Once they've done their job once, then it's fine. If they have to spring back and do it again, you've probably done something wrong anyways. But in this case, let's talk about them as though they're like a gas strut or something with like springy behavior, elastic. So how would you indicate that? Well, you could just say it's a strut and it absorbs some impact force, but maybe that's not the best way to do it. In your physics classes, you always drew springs like this, right? So that would be like a linear spring. Or if you had a torsion spring, you would just pick a point and draw like a little spiral around it. That would make a torsion spring. So you could do things like that. So with the secondary strut and primary strut, we could draw in this little zigzag to indicate that it's some sort of linear spring-ish, and it kind of approximates that behavior. So with the question on your problem set that has springs, you should think about how to best approximate that behavior using tools like this. Okay? So I hope that's a good hint. All right. So let's skip doing this one in like a more general audience drawing because I think you probably get the idea. It's just more detail. Yeah.
Sorry, what's a strut?
A strut. So a strut is it's just a word for like a structural member that I think is meant. It can mean a lot of things. Like it can be like a hard strut that doesn't have any really elastic behavior at all. It's just there to like provide rigidity. In this case, the strut is there to like absorb the impact forces of landing and not damage the rest of the vehicle.
And that's how you know it's like a little elastic?
Yeah, yeah.
Okay. So
Yeah.
it's like just context-based?
Yeah, it's context-based, yes. Yeah.
Thank you.
To the left of the secondary strut, why is there like no branching? Like, why is there like no branch there? In the diagram, it's like a fork, kind of like a branch.
Oh, yeah, like here?
Yeah.
Yeah, so in a kinematic stick diagram, we don't really care about like what the shape of the member looks like, right? So it's also like a 3D mechanism in real life, which is probably how it's shown in the diagram. But I'm just doing like a two-dimensional representation of it. So that's why there's some like extra stuff in that diagram that I haven't drawn here. But the behavior is the same. Yeah?
So you mentioned that these like real life mechanisms are not springy, right? And we just drew in the springs to like
Yeah.
how
I wanted to use this as an example to talk about like how to deal with springs. So I'm just going to say like, oh, it's kind of springy. It like absorbs impact forces. That's what it's there for.
And is there any way of kind of showing that it just like absorbs the impact force without springing back? Or there's no?
I don't know if there's a good way to draw that on a kinematic diagram. You'd probably just want to label it as some sort of like crushing area or something like that. Yeah.
Is it that we will always have a spring in the chart that we'll have to draw?
No, only if the context tells you that that's an important aspect of this mechanism. Yeah.
So just confirming, you were just drawing the springs to show how to do it in general, because I don't see any springs. Is there any indication?
Yeah, so it's not really shown in this diagram, but I was digging into like how these things actually work, and the way the strut operates is there's like a crushing zone of material inside the strut that's meant to like absorb the impact forces. So that's why I wanted to use this as an example to talk about springs. Because springs also crop up in your problem sets, and I know a lot of you are going to probably be emailing me about that. Yeah, question?
Is that length, the longest one, is that not rigid at that joint?
Oh, yeah, good point. Actually, excellent point. So I should draw another thing here. Good catch. To indicate that this whole leg is one rigid body. Yeah, good point. Okay. So I think this is a good segue into mobility. So maybe we can start by calculating the mobility of the backhoe that we just covered. I'll bring this back down. Not come down anymore. Okay. All right, so with mobility, it's actually very procedural, which kind of makes it easier. So once you kind of have like a method, a procedure that you can work through step by step, you almost don't really have to think about it too hard because you sort of know with experience how to just go through all the steps and get the right answer. I find that's the case in a lot of things in engineering. Like once you find out how the procedure works for a certain type of problem, then you don't really have any problems with it going forward. Okay, so the first thing we want to do with mobility is count up all the links. And we've already done that here. We've identified 8 different links. And then we want to calculate or sort of count up all the different connections. So the way that I like to do this is I like to sort of just list them out. Yeah, question?
Would we mark springs as a separate link?
Sorry, can you say the last part?
Similar to hydraulics.
Oh.
Because it does look like there's kind of 2 portions on the leg. I don't know, I'm not certain.
Yeah, I guess it would depend on the context.
Okay.
Like if it was literally just a simple spring, probably not.
Okay.
You'd probably just want to draw it and say it's a spring, but depending on the context, you might want to, yeah. Okay. So we counted up all the links, and so what are the different kinds of kinematic pairs? Does anyone want to shout something out? Turning pair, yeah, that's the most basic one. Sliding. Rolling. And roll plus slide, I heard it. Okay, so when you're doing these problems, if you want to get really procedural about it, you can actually just like make a table. I think in the problem set it kind of leads you in that direction. You can write down all these and just sort of count out how many of each of these exist in your diagram. So with turning pairs, I like to write them out as I count so that I don't accidentally count the same one twice. So turning pairs, we have connection between 1 and 2, right? The ground link to the first vertical link there. That's one of them. And from 2, we have 2 to 3 is a turning pair. 2 to 5. And from 3, we have 3 to 6. 3 to 7. And 3 to 4. And the last one that we haven't counted yet, I believe, is 4 to 8, right? 4 to 8. Okay, so it looks like there's 7 turning pairs, if I've counted correctly. 1, 2, 3, 4, 5, 6, 7, yep. Now, how many sliding pairs? Anyone want to guess? 2? Yeah, there's 2 sliding pairs, right? 5 to 6 and 7 to 8. Those 2 links are able to slide relative to each other. Do we see any rolling pairs? No, right? Yeah, I don't think there's any rolling pairs. There's no roll plus slide pairs either. So if you remember, these first 3 turning or kinematic pairs are 1 degree of freedom kinematic pairs. And the roll plus side is a 2 degree of freedom kinematic pair. So all of these together kind of are part of the same part of the equation, and this one's kind of its own thing. Okay, so what's our equation again? it's 3 n plus 1, or n minus 1, sorry, minus 2 j1, which is, j1 is the 1 degree of freedom kinematic pairs, minus j2, and then minus any redundant constraints, n sub r. Oh, plus, yeah. Sorry. And that's equal to the mobility. Okay, so if we were doing this in this case, looks like we have identified 8 links. So that's 3 times 8 minus 1. And how many 1 degree of freedom kinematic pairs? 1, 2, 3, 4, 5, 6, 7, 8, 9, right? Yeah. Minus 2 times 9. And then we don't have any 2 degree of freedom kinematic pairs or redundant constraints. So 3 times 7 is 21. And minus 18. That gives us 3, right? Our answer is 3. So does an answer of 3 make sense? It does, right? There's sort of 3 different ways that this mechanism can independently move. One is this arm can swing up and down relative to this pivot point down here. One is this hydraulic cylinder can compress and extend, which would raise and lower the sort of boom arm, right? And the last way is that this hydraulic cylinder can compress and extend, and that tilts the bucket. So a mobility of 3 makes sense in this case. You can probably see that just intuitively. But sometimes it's not quite as intuitive. So any questions about the mobility calculation here? No? Okay, good. Okay. Do you guys want to do it again with the landing leg? Yeah? Okay, let's do it again with the landing leg. So we haven't yet numbered the links here, right? But this one's a little simpler. So let's start with the ground. We'll always number the ground as link 1. It's just a convention. And when it boils down to it, it's really just a simple 4-bar mechanism. So we'll just label the other links. Maybe this one's 2, 3, and 4. So turning pairs, sliding pairs, rolling pairs, and roll plus slide. So how many turning pairs? Let's count them out and list them, just to be rigorous. Number 1 to 2, right? And 2 to 3, 3 to 4, 4 to 1. So it looks like there's 4 turning pairs. I don't see any sliding pairs, rolling pairs, or roll plus slide. With the springs, so springs, from a kinematic point of view, it's not really much about like the actuation of the thing. It's more about using the springs to like sort of address the specific demands of this task, right? But from a kinematic point of view, you can kind of consider them as rigid. It's only when you start to talk about dynamics and the forces involved that we would talk about how much the springs are compressing or extending. But when we're just doing a kinematic analysis, a pure kinematic analysis, we aren't discussing forces, right? So the springs aren't really important in that context. So yeah, no sliding pairs, rolling pairs, or roll plus slide. So we can just get right into the formula. So there's 4 links. And there's 4 1 degree of freedom kinematic pairs. And there's no redundant constraints or 2 degree of freedom kinematic pairs. So this is 9 minus 8 is 1. So this device, just like most 4-bar mechanisms, it has a mobility of 1. Yeah?
Why is 2 to 3 a turning pair? Because isn't it all one rigid load? Like,
3 is this link here.
oh, okay.
Yeah, so 2 is just, it's just the connection down to this part that's rigid with link 2.
Okay.
But it's a pivot to link 3, yeah. Yeah?
Why didn't we consider the deployed position fixed, like number 1? Link 1.
Link 1, the ground?
Yeah, why didn't we consider the deployed position? Like, you see how you drew it like a...
Oh, you mean like down here? Why isn't this the ground?
Yeah, why isn't it?
Because you could have it in the deployed position, but the machine's like still floating in space, right? So it's still like movable. And it's not necessarily fixed to the ground. So yeah, just the mechanism of how the leg deploys and undeploys.
This is the actual, like, the deployed position is like the actual thing that you move into the ground.
Yeah, that's what makes contact, yeah. Okay, so I hope that's clear. Okay, so next, oh yeah, question?
If you have a 4-bar, I think it's when the 2 short links are the same length.
Yeah.
You could get that change point where one link could go one way or the other way.
Uh-huh.
Does that change mobility at all?
I wouldn't say so, right? Because remember what Professor Diller was saying in class about how there can be multiple correct solutions, but it still doesn't change the mobility. Like if you define the parameters a certain way, you might say that, oh, it has like 2 potential solutions according to the parameters that I've chosen, but it still only has a mobility of 1, right? Once it's in one of those positions, there's only one way it can move. Yeah?
So to get the number of links for the formula, you can't just count out the number of pairs that you've written out, right? Like that won't work. You have to count out to the number of links that you counted on the diagram, right?
For this part? Yeah, you have to count the links that you've identified in the diagram.
So the pairs that you write down, like you total them up, that's not the same.
So these pairs are for the kinematic pairs, and that's this number here.
Oh, okay.
Yeah, this is the number of links, right? This is the number of kinematic pairs.
Okay.
Yeah.
Why is there no turning pair at the deployed position on your stick diagram?
You mean here?
Yeah.
Okay, I guess you could. If you wanted to, you could. I don't know if that's really accurate. I actually hadn't considered that the foot would pivot, but if it does, then yeah, you could include this as like another link.
That would change the mobility too then, right?
It would. You're right. It would. Because you'd add another link, but only one more kinematic pair, so the mobility would increase by 1. Okay. So something that Professor Diller mentioned in class was redundant constraints, right? Yeah.
Sorry, do you mind explaining again, like the 2 to 3 for the turning pair?
Okay, so you're talking about this thing, right?
No, like the 2 to 3.
Oh, 2 to 3? Yeah, so 2 to 3 is just like a regular turning pair, right? It's just that link 2 extends even further to reach the foot. So this part and this part are all the same body. Yeah, they're fixed together. Yeah. Okay. So Professor Diller was talking about redundant constraints. And I would say that with these types of problems, identifying the redundant constraints is probably one of the harder parts. I'm not sure what the midterm looks like exactly, but if he wanted to give a harder question on this type of thing, it would definitely include redundant constraints. So I'll start with a simple example. Okay, so let's say that I have a ground connection like this and just one stick coming off it. That's fine, right? Everyone knows how to deal with this, hopefully. Well, what if I decided to get a little spicier and added another stick coming from the same point? What do we do about this? So if you wanted to do a mobility calculation of this, let's number these links. So number 1, 2, 3. What would happen here? So the number of turning pairs. This is where it's a problem, right? How do we count the number of turning pairs there? If I didn't draw in this second link, it would obviously just be 1, right? But now that I've drawn it in, what do? Well, maybe we can consider all the links that come in there and all the different ways that they combine in pairs. So I could do 1 to 2, 2 to 3, and 3 to 1. That's one way we could think about it. And if we wanted to do a mobility calculation on this, we'd have our formula, right? 3 n minus 1 minus 2 j1 minus j2 plus n sub r. And if we just did this calculation, 3 times 3 minus 1 minus, we've identified 3 turning pairs here, right? There's no roll plus slide, so minus 0 plus, okay, I'll just leave this as n sub r, foreshadowing. So if we didn't think that there were any redundant constraints here, like if n sub r we just forgot about and assumed was 0, what would we get here? We'd get, this is 6 minus 6 is 0? This device obviously doesn't have a mobility of 0, right? Intuitively, we would think it has a mobility of 2, because each of these links can independently rotate. So what exactly has happened here? So this is a case where you can think about it a couple different ways. The way that I've gotten it here, you could think of it as having redundant constraints, right? 1 to 2, 2 to 3, and 3 to 1. So something in here is redundant. Now, what does a turning pair, what constraints does a turning pair impose? It imposes a restriction on the x position and the y position, right? But it has no restrictions on the rotation angle. So if we just look at this first turning pair, number 1 to 2, we've basically said that one end of link number 2 has to be fixed at this exact point, right? And then if we look at 3 to 1, it says the same thing about link 3. This end of link 3 has to be fixed at this exact point. It can still rotate, though. So then if we add in 2 to 3, what does that say? Well, it says, again, the same thing about one of these links, right? Either it says for the second time that this end of link 2 has to be fixed in this exact position, or it says that about link 3. Something there is redundant, right? We've basically said twice that this end of link 2 has to be fixed at this point. So if, how do I best explain this? Do you guys understand what I'm trying to say here? Like this link is fixed at this point twice by 2 different constraints, or 2 different turning pairs. So in this case, n sub r is equal to 2, because one parameter is the x position and one parameter is the y position, and both of those were redundantly constrained.
Sorry, can you explain that again?
Yeah. It's a bit confusing. I'll try my best. Okay. So let's look at just link 2. Yeah, this is link 2. And let's talk about this point here, which is fixed at the ground. So like this. So turning pair number 1 to 2, the turning pair between link 1 and 2, what constraints does it apply on link 2? Remember those 3 parameters that Professor Diller was talking about? We have the x position and the y position and theta, right? So this turning pair has imposed the x position of link 2 and the y position of link 2 to be fixed. If we're just talking about this point here, theta can still be anything. And that's just what a turning pair is. It fixes a position, but not a rotation. And then if we look at the same thing, but for link number 3, if we look at turning pair, what is it, 3 to 1? It says the same thing, right, about the x position of link 3, the y position of link 3, and theta. So it sort of constrains the position, but not the orientation. So then if we look at link 2 and 3 together, this is turning pair 2 to 3. And we have the 3 parameters. So this is talking about the relative positions. This turning pair, right, is talking about the relative position between link 2 and link 3. It's saying that their ends are joined. The position of their ends is the same. But link 3 is already tied to the ground. So what this is really saying is that link 2 is through link 3 tied to the ground, right? So in combination with this turning pair here, we can say the link 2 is tied to the ground. Even if you didn't know this, even if I covered this up, you'd still be able to infer link 2 is tied to the ground at this point, right? Because it's tied to link 3 at the same point, and link 3 is tied to the ground. So through that chain, it's tied to the ground. But we already know it from here. So now we've constrained x and y of link 2 twice. Does that make more sense? That's why there's a redundant constraint here. So this is kind of like the formulaic way to think about these redundant constraints with turning pairs. Yeah?
So what you mean by 2 redundant pairs is when these x and y on the 2 to 3?
Uh-huh.
So x and y makes them 2 redundant pairs? Or what
So if we talk about the position here, like let's call the point B, right? So point B on link 2 has a fixed position relative to point B on link 3. They're the same, right? But point B on link 3 is tied to the ground. So then we can say point B on link 2 is also tied to the ground. But we already knew that from this one too. So that's why it's kind of like tied to the ground twice, and that's why it's redundant. Yeah.
So I get everything like conceptually. I'm just not sure like in the formula when you write n r equals 2, where are you getting that 2 from?
Yeah, it's these 2 parameters. So remember the talk of like the 3 parameters that define where a body is in space.
Right.
So the x position and the y position, those are the 2 parameters that are fixed.
Right.
It's the position of point B.
Okay. Can we do another example?
Yeah, yeah, we can do more redundant constraint examples. Yeah.
So if we have like already 3 links, the redundant constraint would still be 2, right? X and y.
If you had 3 links connecting to the same spot, it gets complicated very fast. I don't know the answer off the top of my head, but it would be more complicated for sure. Okay, so I'll just tell you another way to think about this problem, which doesn't really involve redundant constraints. There's another way to think about this that's maybe like a little more intuitive. Maybe it works better for some of you. Okay, so let's talk about the same problem, but from a more intuitive point of view. Right? What if I zoomed in on this point here, the ground connection point? What if I zoomed in so I'll just draw here, zoom in. And what if I found that actually they're not really connected at the same point? And instead, they were just slightly apart. So I zoomed in on this diagram over there, and I found, well, actually they're very close together, but not exactly at the same point. That would be easier to think about, right? You wouldn't have to think about redundant constraints. You would just say, oh, like the mobility is 2, and it would be easy to calculate that. There's no redundant constraints there. Basically, we would be saying that this turning pair, 2 to 3, it doesn't exist anymore. But if this distance was like really small, like 1 micrometer, would that affect how the mechanism behaves? No, it wouldn't, right? And in real life, nothing is at the exact same position, right? Like a pin will always have like some tolerance error. It has like some slop or sway, but it doesn't affect how the mechanism operates. So this is one way to think about that problem where you don't have to think about redundant constraints. So I hope that's a little easier to understand. You can choose whatever method works for you. And I would say if you wanted to put this into like a more like a rigorous way to think about it, like not just for this problem, but what if you encounter this in like other problems, you can think about adding links one at a time. So instead of considering all 3 links together, you could just add them one at a time, and each time you add them, you only add 1 turning pair. So if I had link 3 here, I would first say, okay, there's 1 turning pair for link 3, 3 to 1. And then when I add the second link, I only add 1 more turning pair, which is 2 to 1. So adding links like 1 at a time might help you think about it. But redundant constraints can definitely get kind of confusing. And I'll cover more examples related to that. But maybe we should take like a 5-minute break since we've been sitting for an hour. So let's reconvene at, let's say, 11:20. Okay? Okay, guys, so we don't have too much time left. So let's get back to business. Okay, so I know there's a lot of questions and confusion about redundant constraints, which is understandable because I was confused by them when I was taking this course. But the professor will get into more examples about it in class, maybe different ways that you can evaluate redundant constraints. I know he didn't really get into it in the last lecture, but he will. So I'll just give one more example of a redundant constraint. And this will probably be covered in class as well. So don't worry too much if you don't understand right away. So let's talk about the case where there's 2 gears. Let's say we have 2 gears like this, and they're both connected to ground. Now, this is a classic example of redundant constraints. So if we have these 2 gears, we can start by labeling the ground link, number 1. And we can label the 2 gears 2 and 3. And we should probably indicate that at this connection point there's no slip. Right? There's no slip because they're gears, they're meshing. It's impossible for one gear to move without the other one moving as well, unless something breaks, but we're not talking about that. So if we wanted to do a mobility calculation on this, we could start by counting the number of turning pairs, right? So I'm seeing 2 turning pairs. Does everyone agree? Yeah. 1 to 2 and 1 to 3. Sliding pairs, doesn't look like anything sliding, so none of those. Rolling pairs. So 2 and 3 are kind of rolling relative to each other, right? That's what gears are. So there's like one rolling pair here. Okay, so if we were to do a mobility calculation here, we'll just put up the formula again. If we work through this formula, 3 times there's 3 links. We've found 3 different turning pairs, or 3 different kinematic pairs, which are 1 degree of freedom, right? There's no roll plus slide. And we'll just leave n sub r here for now. So what does this give us? Well, if we didn't consider redundant constraints, this would have a mobility of 0, right? 0 question mark? But intuitively, this obviously doesn't have a mobility of 0. We would expect a mobility of 1, right? If you turn one gear, the other moves. If you know the position of one gear, you know the position of the other. So in this case, if we're trying to think about what is redundant here, let's think about the more basic case of a rolling pair. Maybe this is easier to think about, just like a ball or like a tire rolling on the ground, right? And we have our 3 parameters, x, y, and theta. So what is constrained by a rolling pair in this example? So let's say we have a wall here, and that's how we're measuring x. And we can measure the y position like this. And it has some rotation angle of theta. So in a rolling pair, what gets constrained, at least in this example?
Y.
Y? Yeah. Y is constrained. And then the other 2 are kind of related, right? So that relation provides another constraint. So if we come back to these gears, if we draw like an imaginary line down this contact point, what's y in this case? Let's say for this first gear, gear number 2. It's like the distance between the center of the gear and this plane of contact, right? It's like this is like so-called y. I know it's horizontal in this diagram, but it's analogous to this diagram here. And the same thing kind of occurs here, right? So this is also like quote-unquote y. So maybe this starts to give you an idea of where the redundant constraint is coming from. Because these 2 turning pairs, 1 to 2 and 1 to 3, they've already fixed the positions of the center of these gears, right, in both x and y. But if we introduce this rolling pair between link 2 and link 3, that further fixes like this distance, the separation distance between the 2 gears. But we already knew what that separation distance was just from these 2 turning pairs. that's where there's like one redundant constraint, is because the distance between those is like a one-dimensional thing. And so nr in this case is actually equal to 1. So that's why the mobility ends up being 1. And I'm sure that Professor Diller will cover this example again in class or something similar. Does that make sense? No. No? Okay. Okay, I'll try to explain it again. So remember that turning pairs fix the position of a link in space, right? But not the orientation. So this turning pair from 1 to 2, from the ground to the first gear, has fixed the position of this first gear here, gear number 2. And likewise for this turning pair between 1 to 3, it's fixed the position of this gear. So from those two, you would already be able to calculate the distance between the centers, right? But now if we introduce this rolling pair, we're saying, okay, the rolling pair says that the distance between these two gears is fixed. But it was already fixed. So now we fix it twice. And that's why there's a redundant constraint. And the reason that there's only one redundant constraint instead of two is because if you look at this example, it doesn't fix both positions, right? It only fixes one of the parameters, which is this like y, which is the distance between the rolling object and like the plane it's rolling on, right? So that's why this like one-dimensional distance has been fixed twice. Okay, so the last thing I want to cover is just about lab number 1, unless there's any questions. Yeah.
For this case, like the x value at the center is not moving to it.
Sorry?
The x, like the x coordinate of the center is not moving to it. So that's a rule.
Right, but yeah, so this is where it gets a little confusing. So the rolling pair, what a rolling pair constrains is like the normal distance between the rolling object and the thing that it's rolling on, right? If I drew it like this, it would be this normal distance. So it's not really like y. It's only y in like this drawing as I've drawn it. But like in this case, you would think about like this, the coordinate. It's not really clear if this is x or y that's being constrained, right? In this case, because it's at an angle. But what's important is that like this distance is constrained, and that distance is like a one-dimensional thing. I don't know if you guys remember from linear algebra, like change of coordinate systems. Maybe some of you are traumatized by that. But it's the same idea, right? Like a two-coordinate coordinate plane can be transformed into any other like basis of coordinates. So it's like a one-dimensional thing that's being constrained. So this distance between the centers is being constrained twice by all the kinematic pairs that we have.
So like, why isn't the process of adding them one at a time work in this case here?
So yeah. So the reason is because when you add a new gear, you're adding two new things, right? So like we add one gear and it's fine. It makes sense. Like let's say we add this gear first and we don't consider this gear yet. So if we add this one gear, everything's fine. But when we add the second gear, we've added a turning pair and a rolling pair. In this case, the turning pair wasn't like at the same location. And because there's like the reason it worked, okay, just come after the class, I'll explain it. Yeah, I just want to get through one more thing and then I'll explain it to you. Okay, guys. So the last thing is about lab 1. The professor just wanted me to talk a little bit about lab 1. And so if you run the starter code in MATLAB, you get this diagram, right? So he wanted to do like a little discussion about why this diagram like wouldn't be suitable to like put in like a report or something. Like there's things missing from this. Like if you look at this diagram, can you really tell what's going on? Probably not, right? Like what are those two little lines, two little red lines coming off? What does the green line represent? What is B? what's x and y? I mean, x and y are positions, right? But like relative to what? What do they mean? So we want to, when you're doing your lab 1 and like submitting the report, you want to think about how to present the results in like a way that's more understandable. So I just want to like point out a few things here that you may want to like improve. So like the base link, like those two little red lines, it's not really clear what's going on, right? So maybe there's a better way of describing what's going on there. Maybe you could add a label, maybe you could draw it differently, maybe you could do both.
I have a question.
Yeah.
What's the purpose of the base link anyway? What is the two red, the 0.5 line?
Yeah, so it's I think it's to show that that point is like fixed in space. Like is it connected to ground? It just isn't drawn like the same way that we're used to. So that's exactly the point, right? Like it's not really clear like what's going on there. So try to make it a bit more clear when you're submitting your reports. You might want to include like some sort of legend or something to explain like what is this green line? What purpose does it have? And the title, I would say Lab 1, Problem 1 is not a good title for any figure ever. You should probably use a more descriptive title. And you know, if you're presenting this for like a more general audience, like X and Y probably aren't a good choice. Maybe just like, you might want to even omit them entirely if you're presenting this for a general audience. But because you're presenting the report to a non-general audience, then it's probably fine. So anyway, that's just a few quick comments about Lab 1. So we can just wrap it up here unless anyone has any questions. You guys can come down and ask questions. So thank you. Yeah. I'll be here all month.